Hey pre-algebra guys, we're on section 10.6 and 10.7. We're throwing it all together. So I'm going to jump in and try to make this as short as I can for your sake and mine. But we got to still get through it. So chapter 10.6 is permutations. Chapter 10.7 is combinations. What do those words even mean, you ask? Well, they are very, very similar. However, the main difference here is that permutations have an order that matters. And a combination, order doesn't matter. So, order matters, order doesn't matter. Order matters, and order doesn't matter. So, basically what we have is a group of objects, whether they are the socks in your drawer, or the numbers in a telephone number, or the books on a shelf, whatever they are. You can either put them in a certain arrangement, and you can put them in a certain order. That's called a permutation. We're going to recognize this symbol here. We're going to be using that a lot. That's more of our equation, I suppose. And yet a combination then is going to be just putting them together however you want. So order doesn't matter, and we're going to recognize it with this little formula here, and we'll do a little bit more about that as time goes on. So example, you have, I don't know why I keep thinking about socks in the drawer, but let's just throw socks in a drawer, right? Let's say you don't feel like folding them and matching them, so you just throw them in your drawer all together. You could pull 2 socks out, right? And you would have some sort of a combination of socks. Does it matter which order they're in? No, if you get a white one and a black one, you can choose which foot you put them on. Doesn't matter, just you pulled which 2 socks out. Order matters for a permutation. Let's say you threw a bunch of numbers in. Let's say my phone number has all the exact same numbers in your phone number, right? So let's say someone's phone number is 81423456778. Convenient phone number, right? Well, hey, order doesn't matter. These are the numbers in my phone number. This is a combination, so I'm going to dial 423841865 Am I going to get the same person? Not at all. So permutation is an example. I've got a certain number of numbers, but the order really matters. Okay, so that's kind of what we're talking about. We're going to start with permutations. This is 10.6. We're going to cover it really briefly. Okay, so permutations. Let's say we have 3 letters, A, B, and C. We could put them in a bunch of different orders, right? We could say A, B, C. We could say C-A-B, B-C-A, etc. I'm not going to read it all to you. You know how to read. So we could have 6 different ways here. 1, 2, 3, 4, 5, 6. And the way we would look at this is we could say, hey, I know that when I'm putting some things in order, I could just put my first, well, let's create some blanks here. So I have 3 letters, right? And I have A, B, and C. I have 3 letters and I have 3 blanks, okay? So what order? Well, I can pick whatever I want to put into this first blank, right? So let's see. If I were in the classroom, I would ask you which one you want to pick. Let's just pick B because you're not here to help me. If we want to move that first, great. I have 3 choices, right? I have 3 choices here. Now I need to move something into the second blank. Well, I already used up the B, so how many choices am I left with here? Well, I'm only left with 2 choices, so I can move C into there if I want, but now I had 2 choices to choose from there, and now I still have to do something in my last one, but I don't really have any choices. It's just whatever is left, and so in that case, I only had 1 choice. Now, if I were to multiply that, I would come out with the number of permutations, and in this case, it would equal 6. But, right, I could have done this in a lot of different ways, okay? So if we move them back, we could say that I don't want to start with B, I want to start with C, okay? So I'm going to start with C. I had 3 choices, didn't I? Well, it doesn't even matter. I am still left with just 2. Then I put that one in, and you know what? I am still left with just 1 choice. You could do this over and over again. It doesn't matter. You are always going to have 3 choices the first time, and you are going to have 2 choices the second time, and whatever is left over just gets last place. Okay? This is called the fundamental principle of counting. You multiply the number of choices the first time by this second choice by the third choice. And what you're going to realize is whether we started with 5 letters, 10 letters, 26 letters, every single time I'm going to have one less. So I'm going to multiply 3 times 2 times 1. Or I'm going to multiply, if I had 5 letters, I would multiply 5, and then I would have 4 left, and then I would have 3 left, 2 left, and 1 left. If I started at 500, I would have 500 choices. That would multiply it by 499. Then I would multiply it by 498. Now, I am not going to do that forever and always, but I could keep going until I got to 1, right? And every time you put one letter in your new little blank spot, you would have one fewer to choose from the next time. Okay, fundamental principle of counting. These are permutations. The order really matters. Okay, all right. Now, this is a pattern that comes up so frequently in math, they decided to give it a name. It's called factorial, and it's symbolized by this right here. This is an exclamation point, and it is also in math a factorial, which just means, here's the fancy formula for it. All this means is, hey, I've got some number. And then the next thing I multiply is 1 less than that. The next thing I multiply is 2 less than the first one, 3 less than the first one, 4 less than the first one, 5 less than the first one, right? So if I had 5 factorial, I kind of messed this up here. You guys get a freebie here. This doesn't equal anything. I already gave you the answer. Okay. 5 factorial. We already did that. 5 factorial. I keep saying factorial. It's factorial. Excuse me. It's represented by this exclamation point, is equal to 5 times 4 times 3 times 2 times 1. I guess we could actually calculate what that is. And I do want you guys to pause this video and get out your calculators, because you are not going to be doing this stuff by hand. Don't worry. Okay, I'm not going to do that to you. And this equals 120. You could do the math in your head on this one. 20 times 3 is 60 times 2 is 120 times 1. 120. Okay, now this here, I'm not going to actually calculate what this all is, but 7, 6, 5, 4, 3, 2, 1, I didn't skip any numbers. It's going down. I would rewrite this as 7 factorial. Okay, make sense? They all will equal a number. They all could equal a series of products, and they also could equal a number with this symbol. Okay, those are all ways to represent it. I know I'm going quickly through this. Hopefully you're following. Pause the video if you need some help. Okay. This is how we're going to represent it, and we are going to find some calculations, because you may not always start at the very first and come all the way to the last. You might have a number of objects and only take a couple of them at a time, right? So in the past, this other example of the letters, I had 3 different letters, and I took 1 at a time, okay? Well, I might not always do that. I might have 10 different objects, and I might say, hey, I'm going to pull out 2 socks every time, right? If you're talking about socks. In this case, order doesn't really matter, but let's say you pulled something that order did matter. I mean, it would be possible that you would want to take more than one thing at a time, okay? So this is how we're going to represent it, and it's going to be written with this formula. N factorial, whatever this number is here. Oops, I don't want to use this, okay? Put that in the top. This is really a plug and chug. Take this number that's to the left of your P, and put the factorial symbol, and then subtract the 2. Make sure you subtract r from n. R will always be less than or equal to. Okay? Or it's not a permutation. Okay, you can't take 12 socks out if you only have 10 in the drawer. All right, and so you'll subtract them and then do the factorial. So let's do an example of that. Let's start here with 6 objects, and I'm taking 3 at a time. So if you'll note, I kind of said, hey, n equals 6, right? Because n was first, and r equals 3, because r is second, okay? So how are we going to write that? Well, we'd have to look at our formula, and we would say that we have 6 factorial, because it's the n value, okay? N was on the top. I guess I could rewrite this up here, n factorial, over n minus r factorial. So r in this case is 3. Okay, right here. I should make that one yellow to go with the r. All right, so then let's kind of expand this out. If I subtract first, remember you're doing parentheses first, 6 minus 3 gives me 3. Okay, so now I have 6 factorial over 3 factorial. And some of you are going to recognize, hey, some of these are going to cancel out here. You're going to start finding a pattern, but for now, I want you to write them all out. If you can find the pattern already, that's great. 6 times 5 times 4 times 3 times 2 times 1 is 6 factorial. Over 3 factorial, 3, 2, 1. Everything always ends in 1, so you are going to have something that cancels. When I'm multiplying these, it's not different terms, so I can just, like, if I'm multiplying by 1 on the top and by the bottom, and on the bottom, it kind of cancels itself. Okay, so those will all cancel. This gives me 6 times 5 times 4, or 120. Okay, so I guess I should say this here. The permutation with 6 objects taking 3 at a time is equal to 120. All right? Now, I want you to know that we don't always have to take just 3 at a time. It's possible that I just want to know 5 factorial. I just want to know 6 factorial. That's going to be noted with the same number. So if I had this here is 4 objects and kind of how many in a way that I'm taking them at a time, anytime this is the same number, I want you to say, hey, there's a big alert. There should be red lights flashing. You should see a big proceed with caution symbol, right? So just be careful. If they are both the same, then you just have the number factorial. So in this case, it's just equal to 4 factorial. So that means 4 times this is a 3, even though it doesn't look like 1. 4 times 3 times 2 times 1. All right? So what I want you to know, actually, I guess we should do this, right? So this is 12 times 2 times 1. It's 24. Be very careful. It's quite easy if you have the same number, okay? And if you have different numbers, you'll have to follow this pattern. And you'll do a bunch of these on homework, so you'll have a lot of practice. So let's do a word problem here. How many ways can you arrange 10 books on a shelf? Well, I'm going to put all 10 up every time, right? So I have 10 books, but every single time I'm going to put 10 of them up. Okay, so that's just 10 factorial. Are you recognizing? Oops. Okay, are you recognizing? Did your alert go off and you said, hey, big alert, these are the same numbers, so I'm just going to have whatever that number is, factorial, which makes sense because you're going to use every single book every single time. So I'm not going to do all the math on this in my head, but put in your calculator. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Some of you may have a factorial button on your calculator. Look for it, okay? Or use an online calculator that has one, and you can just type this in and hit enter, and it will give you the number even easier, okay? All right, I know I'm going fast. Pause the video if you need. Practice a couple of your homework problems and then come back to it, okay? All right, let's move on to combinations here. Combinations, we said, are grabbing a bunch of things, but the order doesn't matter. So, like the sock thing, doesn't really matter what order, you just pulled some out of your drawer, and that's what you got. If you had a bunch of kids in a class and I needed to choose 2 students from that group, well, does it matter if I say, hey guys, we're all in the classroom and I'm choosing Bob and Sally and we're going to go in the hallway for whatever it is. It matters that I chose 2 students to work on that project in the hallway, but does it matter if Bob walks out the door first before Sally? No, it really doesn't matter at all. So this would be more of a combination, right? Now, if I said, I'm going to choose a first place and a second place from our activity, Bob wants to be first. And then Sally, right? Or Sally wants to be first. That's a permutation. Order matters, okay? All right, so let's talk a little bit more about combinations. They're going to have a different formula. Remember, it has to be something that order does not matter, but you still have the N, the number of objects. You still have R, how many you're pulling at a time. So our formula is just going to be this right here. We are going to take that N value and still use the factorial symbol, and then we're going to take our R value and do factorial, and then we're going to multiply it by what we had in the denominator previously, so the difference between those two factorial. So, as an example, I'm going to back up. I forgot I had this in here. So last time, going back. Last time we had A, B, and C, right? And there were 6 different permutations because the order mattered. What if I had A, B, and C and I wanted all 3 of them? Well, does order matter? No, not for a combination. So there's really only one combination of A, B, and C. Doesn't matter which order, so there's only one way I can have those 3 letters if those are the 3 letters I have. Alrighty. So actually I should have moved this out of the way first, but I didn't, so here we go. The number of combinations of 3 books from a stack of 7. Alright? Now, order doesn't matter which 3 books I pull. Order mattered before when I was putting the books on the shelf, right? But let's say there's a pile of 7 books, and I'm handing them out. I'm just going to grab any 3, okay? So it doesn't really matter which order I grab them in. Whoever I'm giving them to gets all 3 of them. So I'm going to need to use this formula, right? C, oops, this is the wrong pen. Let's try that. C and R. Do you remember what it is? An exclamation point, R factorial times the difference between n and r factorial. Okay, so n in this case is 3, and r in this case is, sorry. N in this case, what are the number of books that I have? Right, 7. Okay, now how many am I pulling? I jumped ahead of myself here a little bit. I'm going to pull 3 at a time. Okay, so n and r. N equals 7, r equals 3. Okay, now I have it written down here already. N is going to go on the top. Use the factorial symbol. I forget I have this pointer. Okay, and then 3 factorial. And then in parentheses, make sure you do parentheses first. Order of operations will never leave you. It will always be around. Let's take 7 minus 3 factorial. So we have to do that first. That's 7 factorial. Okay, so now let's finish this out. That means I'm going to have on the top 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, could you plug this whole thing into your calculator and hit enter? Yes. Now, is that more work than you need to? Yeah, because some of this is going to cancel. All right? So now down at the bottom, I'm going to say that I have 3 times 2 times 1. That was this part right here. Okay. Now I'm going to have 4, this is still times 3 times 2 times 1, which is this part in the denominator. Okay? Now, we're going to be able to cancel some things here. This is going to cancel, this is going to cancel, this is going to cancel, and the 1s are going to cancel. But I don't have any more 1s, 2s, or 3s to cancel, and so, therefore, I am going to have, let's use red, 7 times, actually, you can multiply this out, but what else could I do? Isn't 3 times 2, 6? Let's make this easier on ourselves. I'm not going to have to reduce later, okay? 3 times 2, I could say, is 6, and those 6s are going to cancel. I'm glad we saw that. Okay, so 7 times 5 over 1 is all I have left, so take a minute and look at that. And then that's really just going to be 35 over 1. Oops, 35 over 1, or just 35 different combinations of books, right? Different combo deals. Okay, so that is what you do with a combination. You are most likely going to have different numbers. It's not the same way with a permutation where you have just one at a time, although that could happen. What would happen if I pulled 3 is kind of like with my ABC. Let's say I had all 3 numbers and I wanted to take all 3 of them. And order doesn't matter, so how many combinations did I say I had with my ABC? I just had 1. Anytime the number for a combination is the same here, it's going to equal 1, no matter what you do. Okay? Now, most of ours aren't going to be that way, but if you see the same thing, hey, just 1. It doesn't matter how many you have. If you're taking them all, there's only one way to combine them together into that one group of everything, because the order doesn't matter. All right. Well, I think you are all set and squared away for taking a look at combinations and permutations. You have a section of homework from each portion, so 7.6 and 10.7. Do your best on these, check your homework, and tomorrow we're going to jump into probability.